Morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make chemistry part of your day. We're going to work on introducing the idea of stoichiometry, and we'll start conceptually, build in the math, and then this will build and build and build over a series of lectures. And we will use it over and over again in different varieties of ways throughout all of chemistry, not just Chem 101. All right, so let's just start with the basic idea, and you can see my awesome drawing ability at work here. We have 10 car frames, you can tell by the beautifully built rectangles, and we have 20 tires, slightly better drawn. And if I said I had 10 car frames and I had 20 tires sitting in a warehouse, and I asked you how many cars can you roll out, most people do just fine with this question. They don't even have to think too long. They're like, oh, this is easy. 4 sets of tires, car, 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 car. We got 5 cars out. Piece of cake. And if I ask you, well, what's left at the end, you might have to think a little bit and say, well, we made 5 frames, we start with 10, so there's 5 left, right? Or we might even call that excess. Left in excess. And usually people do fine with this. And you'll see all kinds of examples online. You'll see making sandwiches and all. Those are people really like sandwiches for explaining this. So cars, sandwiches, whatever. But all of a sudden, if I change this and I make it into a chemistry question and I say 1 car frame plus 4 tires creates 1 car, and instead of 20 and 10, I use 0.75 and 0.230, all of a sudden this becomes an intimidating question. So what are we doing mathematically here with the tires and the frames without, almost subconsciously, without consciously realizing what we're doing? Well, we're basically using a ratio, and I'm going to put this in chemistry terms. This idea that 1 frame needs 4 tires and we get 1 car. So that's the basic premise. Now we make a chemistry and we say 1 mole of frames. Again, mole is just an amount. So if it's 1 frame, it's also 1 mole of frame, or 10th, or 20, or whatever you want. But 1 mole of frames is used every time 4 moles of tires is used and 1 car can be made. So this is really important because we're going to look at this chemically, and the reactants are going to be used and the products are going to be made. So we can do the exact same calculation. It looks exactly the same on your piece of paper, but it means 2 different things. And actually, potentially, it could really mean 4 different things. So let's take a look at what those 4 things would be. So we're going to call this, I call this a mole-to-mole ratio. The fancy word is stoichiometric relationship or stoichiometry. I still like mole-to-mole. It's a little bit easier to say. And it's more indicative of what we're really doing. We're making a ratio of moles, so moles to moles. So this same idea, and I don't even want to worry about the math, I don't want to worry about balanced equations or any of these other things, but there's really 4 possibilities we could do. We could compare one reactant to another, we could compare one product to another, or we could look at, if we start with a reactant, how much product do we get? Or, if I want to make this much product, how much do I need to start with? These are 4 very basic questions that get asked all the time in chemistry or in anything where you're doing reactions. How much do I need? How much can I make? How much do I need of each thing? If I make this, what's my byproduct? These are things. These are very, very practical questions. Okay. So what does it mean? So remember, when we're doing these calculations, typically we're crossing out a unit here. So the one on the bottom is what we're starting with, and then the one on the top is what we're ending up with at the end of the calculation. So from a flow standpoint, it's going to be the bottom to the top. So we're comparing reactant B to reactant A. If you're doing a calculation that ends in a reactant, it's how much is used up. So reactants are used up, and products are made or created. So this is one where the amount's going down. This is how much it goes down by. This is how much it goes up by. And this causes confusion because typically when we start a reaction, we haven't made any product yet. So the number we calculate here is actually the amount that's left. Where this is not the amount that's left, or an amount you could actually measure directly, it's an amount that disappeared. And it could disappear to 0 or maybe not. So when we compare reactant B to reactant A, what's that really mean? It's the amount of A that we need to react with that much B. And again, assuming perfect reaction. If we're going reactant to product, which is probably the most common of all these calculations, is if I start with this, how much product do I make? And again, this is ideal. It's if it's completely reacts, so this is a perfect yield, if you will, or theoretical yield. Product B to product A, that means if I make them as much product B, how much product A do I get with it? And lastly, product to reactant, if I make this much product, what's the minimum amount of reactant I need for that amount? So what's this look like in practice? So, fairly straightforward example here. 20 grams of hydrochloric acid is reacted with excess nickel. How many grams of nickel chloride or nickel 2 chloride is produced? So I want to point out a couple of things here before we get into the nitty-gritty of the actual calculation. Number one, the only number we're given has to do with the chemical hydrochloric acid. What we are asked to produce something about on the end is nickel chloride. You will notice those are two different chemicals. And if you had me in a traditional lecture setting, you would get almost bored or column response where I go, the only way to go from chemical A to chemical B is through, and I'll pause and the whole class will say it back to me. They'll say mole to mole ratio, and I'll say the only place you can get a mole to mole ratio from is, and I'll pause and the whole class will say balanced chemical reaction. We don't get there day one, but by day 2, day 3, day 4, end of the semester, man, they got it. Even years later, some of my students, no problem. So, but this is a huge, but I want to point this out. Two different chemicals. The only way to compare chemical A to chemical B is from that last slide, where I had all those different possibilities. Doesn't matter which way we're comparing, it's two different chemicals. You have to use a mole to mole ratio. This means two things. A, the number one goal of the numbers you're given is convert them to moles. Can't use a mole to mole ratio if we don't have moles. So if all else fails in chemistry and you don't know where to start, convert everything to moles. You're probably on the right path. Number two is, if we see this, we need a balanced chemical equation. A lot of times, particularly at the Chem 101 level, at the introductory level, we'll give you the reaction. But sometimes you do have to write it for yourself. So just to point that out. So if you see two different chemicals, your job is to get the numbers, get them into moles, and find a balanced chemical equation, or write it yourself. Somehow get there. Those are the two key points. So again, chemical A, chemical B must be a mole to mole ratio. That must come from a balanced chemical equation. Okay, so here's our balanced chemical equation provided for us. And what I like to do in these problems, from a help order my thoughts idea, is to pull all the numbers I'm given and put them in columns under each of the chemicals. So if we look at nickel, the only thing it tells us is we have excess. So you might leave this blank, but I thought I'd put excess here just to emphasize that point. Hydrochloric acid tells me I have 20 grams. Nickel chloride, it asks me at the end how many grams. That's always important to know where we're going. And then hydrogen we don't have any information on, which is good. It probably means we don't have to worry about it for this problem, which is correct. And in blue down here, I put the formula weights. And again, hopefully you're getting good at this from the periodic table. The mass of one hydrogen plus one chloride. This is the mass of one nickel plus two chlorides. And again, for my class, 2 after the decimal is great. If your teacher tells you something else, then do that. All right, so you can see very clearly we have to go from one column of information to another. Mole to mole ratio. If I'm being redundant, it's intentional. And that will have to come from my balanced chemical equation. So let's just start with the number we have, 20 grams of HCl. And as I just said, we can't use a mole to mole ratio without having moles. So our first order of business is, do we have a relationship between grams and moles? Absolutely yes. So I'm going to put moles of HCl up here. That is our formula weight, molar mass. And I'll put that in here. Now we have moles of HCl. Once you have moles of HCl, by all means use the mole to mole ratio. And how do I know which of all these combinations of stoichiometries to use? We'll use the two they asked about. They asked about HCl. They asked about nickel chloride. Remember, it's an implied 1 in front. We're just going to pull those numbers. Moles of HCl is on top. Write moles of HCl on bottom because we want to cancel that out. And then on top goes the other one, the one we're asked about. Now we got our nickel chloride. And these numbers, this is 2 is with HCl, so we put a 2 with HCl. There's a 1 with nickel chloride. We put a 1 with nickel chloride. So that now we've converted from HCl. See, all these are tops and bottoms should be the same label unless you have a mole to mole ratio. This is mole to mole. We go from HCl to nickel chloride, which is great because that's what we're asked about. And we have moles. It asks us about grams. Do we have a relationship between moles and grams? Absolutely. And hopefully it's becoming obvious now when I told you not to put grams and moles, but grams of something, moles of something. It's important. They don't all cancel out with each other. They mean different things. And remember, it's a whole bunch of grams per 1 mole. Let's do that. At this point, it's just plug it into your calculator and get a number. Multiply the tops, divide the bottoms. And I got 35.5 grams of nickel chloride. In that, just to summarize, and then we'll call it a day on this video. Just to summarize, number one, we need to get moles. Use our relationship from our balanced equation to get our mole to mole ratio, as I like to call it. And then do whatever the question asks us for. In this case, it asks for mass, so then we do the back end. But this is the general, this is all we're doing. There's only a few things we're doing here. We're doing them in every way possible, but only a couple things. So just take a deep breath, practice this, get good at this. This flow, this structure is really common. Thank you so much.